So we're going to talk now about implicit differentiation, which is basically just taking the derivative when y is not isolated. So like in a typical question, y is isolated, and you take the derivative dy dx by analyzing each variable x and differentiate it with respect to x. But you know, something like this, x squared plus xy plus y squared, you know, it doesn't have y isolated, and furthermore, it's really not easy to isolate y in an equation like that. It's not really a function, right? If you look at what this looks like, it's kind of like an ellipse, but sort of rotated to the side. And you can see it clearly isn't a function. And yet, despite the fact that it isn't a function, I mean, it still has a tangent, right? So we still have a tangent AC, and you can draw, you know, a tangent that has a slope. And so like there's still the idea of finding how y is changing as x changes at that moment. It's just not a function and therefore works a little bit differently. So implicit differentiation is the idea that you can look at an equation that has different variables and try to find either, you know, dy dx or dy du or du dy or whatever. Remember that basically the d on the top, d whatever's on the top is what you are differentiating. Whatever's on the bottom is what variable you know, you're asking how does the top change with respect to the bottom. So for example, dx dx is equal to 1 because however you change x on the top, x on the bottom would change the same way and you get 1. And the same reason dy dy is 1 and du du is 1. How you change the top and how you change the bottom is identical, so their rate of change is 1. Now again, the rules that you know about, you know, quadratics or with powers also work. D of x squared dx is 2x because, you know, you use the power rule. Same thing here. If you're doing the derivative of y with respect to y, then y squared has a derivative of 2y. Now, when you're doing the derivative of, you know, a different variable, so that this one is asking the derivative of y squared with respect to x, the idea is that y squared is a function of x, and therefore the derivative of y squared, and just write this with me, the derivative, so if we go d, let's just put it in this formula. Okay, so the derivative of y squared with respect to x is like, just like if you were asking what's the derivative of some function with respect to x, the idea would be you'd use the chain rule, right? And you would say that the derivative of y squared is 2y, right? You bring the 2 down and then you copy the y, and then you take the derivative of y. Now, of course, we don't know what that is, so we're going to say dy dx, whatever the derivative of y is. Remember, dy dx is another way of writing y prime. So the derivative of this one, you know, derivative of y squared with respect to x is 2y dy dx. Here you would get 3x squared dx dy, right? Because you're differentiating with respect to y. And this last one, you're differentiating with respect to u. So the idea here is just that x and y, both of them are functions of u. So if we're going to do this one, we're going to go du, sorry, of xy, right? It would be, you're taking the derivative of x and y, but with respect to u, so you know, they're both functions. So the product rule says you do x, right, times dy du plus y times dx. Oops, sorry, dx du. Right, so again, it's the same thing as like what you're used to with the primes. It's just you can't really say it's y prime or x prime because you don't know what variable you're differentiating. What's the variable you're actually differentiating here? In this case, the variable I'm differentiating is u. So if I wanted to differentiate this, it would be x times the derivative of y with respect to u plus y times the derivative of x with respect to u. So basically, this is just a way of differentiating different functions that may use different variables. So basically, when you're doing this, okay, your goal is to differentiate both sides of the equation using, dx as your variable. And then you're going to get a whole bunch of terms that have dy dx on them. And the idea is you're going to collect all those terms to one side and then factor them and isolate them. And the idea is to get an answer that doesn't have dy dx in it. So you have dy dx on one side, and you have an expression involving x squared and y squared on the other. So, here's a really good example, right? It says x squared plus y squared equals 4, and then we are finding dy dx. So let's just start this over again. And let's go x squared plus y squared equals 4. And the point here, it doesn't show, but the point it's looking for is 1 and square root 3. So let's just graph that point. Remind you that point is in fact on the circle, right? Because it has a distance of 2 away from the center. But this point must have a tangent. You can imagine what the tangent would look like here. If we draw a tangent that passes through point A that passes the circle, we know that this tangent has a slope of negative 0.58. But how could we determine that using this idea of implicit differentiation? Well, what we can do here is we can say, if we start with the idea that x squared, we're looking for, again, d of dx of x squared plus y squared equals 4, right, is the idea. We're trying to differentiate this entire equation. Now, you can do this the same way that you're used to doing it. Take the derivative of x squared. Okay, so that's 2x, right? Then you take the derivative of y squared. Okay, so that's 2y, but it's a chain rule because y is a function, so we do have to do dy dx. And then on the other side, of course, the derivative of 4 is 0. So the crucial thing in this is to realize that you can differentiate y directly. You just have to treat it as a function and make sure that it spits out a dy dx for its derivative, right? And now we're looking at something where you can isolate dy dx. And remember, dy dx is the slope of the tangent at that point. So, if we just take this same equation and we go 2y dy dx equals negative 2x, right? Can divide both sides by 2, so just do that quickly. So we get this, y times dy dx equals negative x. And then we get the idea that dy dx is equal to, just make sure this works, dy dx, right, simply equal to negative x over y. Sorry, I've just got to type it like this so it shows up properly, right? So we've isolated dy dx. It's negative x over y. Now let's go back to the point we were interested in. The point we were interested in, x was 1 and y was, square root of 3. So if I take this formula and I say slope, let's make a new letter called m, we'll just call this the slope, is equal to negative 1 over the square root of 3, which is what my dy dx equation says. I get this idea that m is 0.58. Now I need a line, okay, that passes through the point I want, A, and then is parallel to this slope, and I can create the tangent to a circle, even though a circle is not a function and therefore not differentiable by your usual rules. You can still create the tangent to a relation like this one if you manage to isolate dy dx, and it still means the same thing it always meant. It means the slope of the tangent at that particular point. Now you have to be careful because the point, there are two places on this function when x is 1. So usually you need an x and a y to specify, not just an x. So this is what it's saying here. Values of the independent and the dependent variable are usually needed to evaluate. Let's try one more complicated one, and then I'm going to leave the rest. And if you want to try them or you're interested in maybe doing this question on the test, then you can ask me some questions about it tomorrow. But let's try one more difficult one. So here we're looking at this curve, 2x to the 5 plus x4y plus y to the 5 equals 36, and the point we're interested in is 1, 2. So let's start this over again. Let's graph the point 1, 2, and then let's draw this. So 2x to the 5 plus, x4, x to the 4, x to the 4y times y, plus y to the 5, and this is all equal to 36. Now this of course creates a really sort of interesting and bizarre curve where it's kind of like a straight line with this like step knocked out of it. Kind of does look like it might be a function, but it's hard to tell based on what we see here. In any case, we can still use our tools of implicit differentiation to take its derivative, right? So we go 2x to the 5 plus x to the 4 y plus y to the 5 equals 36. Now again, we want to find d of this function. We'll just call this u for making this simple. We want to find d dx of that entire thing, right? Is what our sort of goal is here. So just put this up here. Okay. Now to do that, you take the derivative of each part like you normally do. Start with the 2x to the 5. We get 5 times 2, which is 10, x to the 4. Okay, the middle term is a product rule. So we're going to get y times the derivative of the x part, right? So 4x cubed. And then we're going to get plus x to the 4 times the derivative of y. Now the derivative of y, we don't know it, right? So we write dy dx. And then we have at the end, we have the y to the 5. So we get 5y to the 4. 5y to the 4 times, again, that fraction dy dx. Dy dx. Okay, and this is equal to 0 because, of course, the derivative of 36 is 0. Now you're looking at this, and this is a little different than anything we've done before, but it's not that difficult if we just think, okay, everything with an x or a y that doesn't have a dy dx needs to go to the right. Everything with a dy dx is going to stay on this side. Let's just copy this for a second. We'll start a new text underneath it. Get rid of the first line. And so, what we want to do here, we basically want to get the 10x to the 4 and the y times 4x cubed. We want to get those to the other side. So we'll make them negative and put them on the other side. Okay. Then what we want to do is we want to factor the dy dx as though it was a number, right? And we get x to the 4 plus 5y to the 4. And this is equal to negative 10x to the 4 minus y 4x cubed. Okay, and then we can isolate dy dx, right? So fraction dy dx. And we just, all I'm going to do here is send this thing over to the other side. Okay, just move this down a bit so we can see a bit better. Actually, I'm going to pause this here and I'll pick this up on the next clip.